Am I audible?
Yes, ma'am.
Yes, madam.
Okay, ma'am. So all of you can see, we have seen those examples. I think you can read now the questions. Can you? Is the screen visible?
Yes, ma'am.
Okay. So we have seen these examples, how to find the radius of convergence. For that, we have to take the ratio of the next term to the previous term. We find its limit as n tends to infinity, and whatever limiting value we are getting, its reciprocal is the radius of convergence. So I think you are quite now familiar with this kind of thing. Let us move ahead. So I would like to just recall the Taylor series. Taylor series always you write as what? F of x is equal to f of x naught plus f dash of x times x minus x naught raised to 1 plus f double dash at x naught upon 2 factorial into x minus x naught square and so on. So in compact form, we can write the Taylor series as this. So once you read it properly, what is given? Taylor series about x naught. It comes out to be summation n running from 0 to infinity, nth derivative of f at x naught upon n factorial times x minus x naught bracket raised to n. So टेलर सिरीज तुम्ही पाहिली, आपण काय करतो दरवेळेला की nth पॉवर जिथे असेल तिथे nth डेरिव्हेटिव्ह आहे ऍट दिस पॉइंट एक्स नॉट आणि डिवायडेड बाय n फॅक्टोरियल आहे. आणि महत्वाची गोष्ट म्हणजे n स्टार्ट्स फ्रॉम 0 ऑनवर्ड्स. त्याला म्हणतात टेलर सिरीज. इज इट प्रॉपरली विजिबल? In first year, you have seen the Taylor series expansion of e raised to x is summation n equal to 0 to infinity x raised to n upon n factorial. आज पण मी वर्गात तुम्हाला सांगितलं की e raised to x काय असतो? I hope you remember it. E raised to x is equal to 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus and so on. I hope you remember this. So this is power series expansion of e raised to x. Then you have sin x series. Sin x series goes with odd number. So sin of x is equal to x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial minus x raised to 7 upon 7 factorial plus and so on. Then you can talk about the expansion of cos x. Expansion of cos x is, it contains only even degrees. So 1 minus x square upon 2 factorial plus x raised to 4 upon 4 factorial minus x raised to 6 upon 6 factorial plus and so on. So these are the basic series you must keep in mind. These are Taylor's power series. So please take the screenshot of the same. Hope ready for the next. Yes or no?
Yes, ma'am.
Okay. So you can see those in summation sign. Those series you can see in summation sign. E raised to x you can write as summation n running from 0 to infinity, x raised to n upon n factorial, and it is true, the radius of convergence is infinite. So this is convergent throughout the real line. Same is true for sin x and same is true for cos x also. The expansion of sin x, contains alternate plus minus sign. So you have minus 1 raised to n. X raised to 2n plus 1 talks about oddness. These are odd terms. And upon you are having 2n plus 1 factorial. In case of cos, you are having minus 1 raised to n, x raised to 2n upon 2n factorial, and n starts from 0 onwards. Now you can see 1 upon 1 minus x, which always we require. You know the expansion of 1 upon 1 minus x, which you have already used. 1 upon 1 minus, I think, d. You have written as 1 plus d plus d square plus d cube plus and so on. Have you used this? In our first chapter, you have used this as a short method. You can see this is nothing but summation d raised to n. And your n starts from 0 to infinity. N starts from 0 to infinity. Are you getting my point? You have also used the result 1 upon 1 plus d. And how is the expansion? 1 minus d plus d square minus d cube plus and so on. I suppose you know this. So that in terms of x, you can write in this fashion. So this is nothing but summation n running from 0 onwards. And this is d raised to n. but there is minus an alternate, it occurs. So I have to write it as minus 1 raised to n in the beginning and then write d raised to n. Is it fine? Got my point?
Ma'am.
Okay, then I would like to continue. Now let us see the uniqueness of power series. So if the power series f of x equal to summation n equal to 0 to infinity a n in bracket x minus x naught raised to n has a positive radius of convergence, then a n is always equal to nth derivative of f at x naught upon n factorial. What this means? The power series is nothing but the Taylor series. So they are coinciding. Power series of f of x is the same as Taylor series of f. But when, if f has positive radius of convergence, then and then only it will happen. Okay. So you can see as far as 1 upon 1 minus x is concerned, its power series is this one and radius of convergence is from minus 1 to plus 1. Okay, radius is 1. All right. Now let me move to the next. Now there is a theorem. Summation n x minus x naught raised to n is equal to summation bn x minus x naught raised to n for all x in an open interval that contains x naught, then naturally an has to be equal to bn. It is very damn sure. And the next slide, next part says that if summation an x minus x naught raised to n is 0 for all x in the open interval that contains x naught, means every an has to be 0 for all n. Now there was a question about Maclaurin series for cos hx. Question was, find the Maclaurin series for cos hyperbolic x as a linear combination of Maclaurin series for e raised to x and e raised to minus x. So we know cos hx is e raised to x plus e raised to minus x upon 2. And let us use the Taylor series for e raised to x, and hence it will be for e raised to minus x this way. We use this formula then. So cos hx will be summation n running from 0 to infinity. X raised to n upon n factorial is common in both the cases. And the coefficient of this here is 1. The coefficient here is minus 1 raised to n. And we have to half it. We are dividing by 2. So 2 comes over here. Now let us see what happens. If I put n equal to 0, 1 plus minus 1 raised to 0. Minus 1 raised to 0 is 1. So 1 plus 1 will be 2. If I put n equal to 1, this will be 1 minus 1. So 0. For n equal to 2, it will be 1 plus 1. So 2. And for 3, 1 minus 1 makes it 0. Meaning, whenever it is odd, the sum goes to 0. And whenever it is even, the sum goes to 2, but divided by 2 makes it 1. So, cos hx will be summation m from 0 to infinity. There will not be any odd terms, odd powers. All powers will be even. So we are writing it in the fashion x raised to 2m, and upon it will be 2m factorial. So I feel you got the power series expansion of cos hx. I have shared this document to you already. I hope you can go through. Next, I move to how to solve a differential equation as a power series solution. So, in this case, question says, find the power series solution of the equation x square plus 1 times y double dash plus x y dash minus xy equal to 0 in powers of x. In powers of x means x minus 0. So we have taken y is equal to summation n running from 0 to infinity an x raised to n. Now we differentiate this. We have seen this in the morning. If I differentiate this, y dash will be summation from n equal to 1 to infinity n an x raised to n minus 1. And y double dash will be summation n from 2 to infinity n into n minus 1 into an x raised to n minus 2. How it happens that we have seen in the morning. If you want it, we can go y is here. We are saying y is summation and running from 0 to infinity an x raised to n. Now summation stands for addition. So we know the derivative of the addition is addition of the derivatives. So there is no problem. I go for the first derivative. This will be summation, of course. N will come down. So it is n times an, the coefficient remains as it is. And x will be raised to n minus 1. We know the index is reduced by 1. And one more thing, the initial term was a constant term. So its derivative goes to 0. So n will start from next. That is n equal to 1 to infinity. This is very damn sure. Now go for y double dash. What will happen to y double dash? Again on the same lines, summation will start from the next step. So n will go to 2 now. And it continues. Then n was there as a coefficient. N minus 1 will come down again as a coefficient. There is no change in an, so an remains there. And the power of x is reduced by 1. So it gives you n minus 2. This is the usual nature, and that is what I have shown over here. Y dash is n an x raised to n minus 1, and y double dash is n running from 2 to infinity n times n minus 1 an x raised to n minus 2. Now we are required to solve this differential equation. So let us put the value of y in this equation. And to get the solution means what? Either get the relation between a's, the coefficients, or get directly the values of a's. So let us go. We put the values x square plus 1 as it is. Y double dash, as we know, starts from 2 to infinity. The coefficient is n into n minus 1. An remains as it is, and the power of x is reduced by 2. Next, what you see is x is there. Summation starts now from n equal to 1 to infinity. Already we have seen this here. N times an x raised to n minus 1. And minus, there was x. So I have written x, and y we have replaced by the series. And right side is 0. So right side is 0 here. See, there are varieties. This x is raised to n minus 2 here, and outside is getting multiplied by 2 terms. One contains x square, other is constant. In this term, the series contains x raised to n minus 1, and outside it is multiplied by x. And here, The series is x raised to n kind of series and multiplied outside by x. So what is going to happen? This will be summation. I multiplied by x square inside. So n into n minus 1 as it is. Summation starts with n equal to 2 onwards. That is also as it is. X square multiplied by x raised to n minus 2 becomes x raised to n. Then by 1 if I multiply, it remains as it is, as you are watching. It remains as it is. Next comes is x multiplies n running from 1 onwards, n into n, and x will get raised to n. Minus, again I multiply by this x inside, so it is an x raised to n plus 1, and right side is 0. Now we rearrange those terms, because if they are of the same pattern, then only we can discuss, otherwise we cannot. So what we'll do is, we'll try to bring x raised to n everywhere inside the power series. Here it was x raised to n, so this term is as it is, I have written. Is this going fine? Are you getting me?
Oh, madam.
Okay. All right. So I have taken this as it is, and I want to discuss about this n minus 2. As we have discussed in the morning, n minus 2, if I put as k, of course this I am doing in mind, then what will happen to n? N will be k plus 2. But I want this in terms of, I want this to be n. So I'm putting n as what? N plus 2 everywhere. If I put n as n plus 2, so n will begin with 0. In place of n, I'm writing n plus 2, and your right side is equal to 2. Are you getting my point here? So if I put n plus 2 is equal to 2, what will happen? This will be n equal to 0. So I hope you are watching here. N is equal to 0. Up to infinity, so there is no question in the upper side. Now, this n I have replaced by n plus 2 as you are watching. Here also I have replaced this n by n plus 2. So n plus 2 minus 1 makes it n plus 1. So followed this. And this an will now be a suffix n plus 2. And this n minus 2 will take the value n. So I got this to be x raised to n. Did you agree?
Oh, madam.
Now, this is as it is, so I copy it. Next, here I want, in place of n plus 1, I want n. So again, the same kind of thing I have to perform. So what I'll do is, in place of n plus 1, let me put, I think I should have, okay. So in place of n plus 1, I want n. For the time being, let me call it as k, as we have discussed in the morning. So n is going to be k minus 1. But this k is nothing but n as per our discussion. So this will be n minus 1. So wherever there is n, I'm going to replace it by n minus 1. So let us see what has happened. If I put n as n minus 1, I got here n minus 1. If I put n as n minus 1 here, it becomes n that I got. And here in place of n, if I put n minus 1, it becomes n equal to 1. So I hope all of you agree with me. Now what has happened? I just sum these terms up. To sum up, I have to start with the same kind of thing. I see here it is n equal to 2. Here it starts with n equal to 0. And these two start with n equal to 1. Everywhere I want the same starting. So let me start with n equal to 2 everywhere. So this term I keep as it is. Here, let me note down n equal to 0 and n equal to 1 separately. If I put n equal to 0, what will happen? 0 plus 2 is 2 and 0 plus 1 is 1. So 2 into 1, I got 2. A suffix 0 plus 2, it will be a 2 and x will be raised to 0 plus. Now I am putting n equal to 1. So this is going to be 3 and this is 2. So 3 2s are 6 I got. This is a3 and x will be raised to 1. And the remaining term I carry from n equal to 2 onwards as they are. So this particular sum is split into 3 terms as you are watching. Twice a2, x raised to 0 is 1. So it's a constant. 6a3x, and from n equal to 2 onwards I have this term. Hope you are following. Now I move ahead with this. For n equal to 1, I'm going to get 1a1 x raised to 1. So I got a1x. And from n equal to 2 onwards, I keep it as it is. Now minus sign for this. I put n equal to 1, so it becomes a0, x raised to 1, so x, and minus the remaining sum from n equal to 2 onwards. Now we can combine them all. What we can do? Constant terms together, linear terms together, and all summations together. So this twice a2 I have recorded. 6a3x and this a1x and this a0x I'm combining. So in bracket I got 6a3 plus a1 minus a0 x. And now plus summation n equal to 2 to infinity. We are combining all the terms. So all coefficients of x raised to n are taken together. This is n into n minus 1 an. Then it is n plus 2 into n plus 1 an plus 2. This is n an. And this is minus a suffix n minus 1 times x raised to n is equal to 0. And just now we have seen the theorem. Whenever such kind of thing comes out to 0, every coefficient is 0. Just now we have seen the theorem. We have just stated the theorem. I would like to take you back over here. I think, yes, it is here. What you see here, summation n equal to 0 onwards, an x minus x naught raised to n is 0, then an is 0 for every n. So every coefficient will equate to 0 only when the right side is 0 compulsorily. So let us go with it. And we are equating the terms. So I said equating like terms, we get constant I got twice a2 equal to 0 will mean a2 is 0. Linear term, the coefficient was 6a3 plus a1 minus a0. We equated it to 0. So always we will take the letter in terms of the previous ones. So the letter one is a3. I can write it as what? a0 minus a1 upon 6. And now in the summation sign. Summation sign starts from n equal to 2 onwards. So we said for all n greater or equal to. And I wrote here n times n minus 1 an plus this plus n times an and minus an minus 1 is 0. Now I see an appears twice here. So let us combine. Remaining terms are occurring only once. So this term as it is. Then combining a and together, n is common in both. So n is taken common. Inside we are getting n minus 1 plus 1 an and minus a n minus 1 as it is. So what will happen here? Minus 1 plus 1 get cancelled and this is n square an. And always we write the later one in terms of the previous ones. So this thing I have kept to this side only. These two terms I transfer. This was negative, so it has turned positive, an minus 1. This was n square an, so it becomes minus n square an. And then divided by this coefficient. So I got a rule here. Now, I want to write the solution. So let us put n equal to 2. What do we get? A4 is equal to, this will be A1 minus 2 square means 4, A2 and upon 3 into 4 means I got this to be A1 upon 12. Why? Because the value of A0 we have got already 0. Okay. What next? Go with n equal to 3. So it is A5 equal to, again we are putting the values and we'll calculate. It becomes minus 9 upon 20 A3. What we know is A3 is A0 minus A1 upon 6. So that value I have put here, A0 minus A1 upon 6. Actually I have split the 6. So 3 gets cancelled over here and I got this to be minus 3 upon 40, A0 minus A1. Same I did with A4. I got the things in terms of A0 and A1 again. And now putting those values back in our required polynomial or series. So A0 as it is, value A1x as it is, A2 was 0, value of A3 already we have got, value of A4 we have got, that of A5 we have got and so on. Now what we will do is, we can see either we have got A0 or A1. So collect all A0 together and all A1s together. So this is the power series solution of the given differential equation. Have you got it? So I'm sharing this document to you. I hope you'll do it. And on your own, if you try to solve the things, it will be quite better for us. Okay. Pradnya, have you got it?
हो मॅडम कळलं थोडं थोडं ऍक्च्युली उशिरा जॉईन झाले.
Uda?
Yes, ma'am.
Okay, ठीक है. So I have kept this sheet open in front of me. I think you are capable of, we have dealt with this. We have dealt. So you were to talk about this too, no? Third we have taken. And you can, I think, find out the power series solution of these three equations. Hope you'll try. Okay? And I'll help you with the remainings. Is it fine? Okay. So for the time being, I would like to stop here itself. And I would like to share this video to you so that you can once again prepare for the same.